All right, so welcome back, everyone. We had a fantastic first session, and we're looking forward to this second session today on wearables and exoskeletons in prevention through design. So I'm pleased to introduce Mike Flowers, who is an active prevention through design advocate and former president and CEO of the American Bridge Company. Mike received his Bachelor's of Science in Civil Engineering from West Virginia University and his Master of Science degree from the University of Pittsburgh. Mike brings over 44 years of experience in the engineering and construction of high-rise buildings and complex bridges. Mike, the session is yours.
Thanks for that introduction, David, and want to welcome everyone to the 2022 Prevention Through Design Workshop and to session number 2, Wearables and Exoskeletons in PTD. This session will have 3 different pre-recorded video presentations followed by a live expert Q&A session. Questions can be submitted throughout through the Q&A function at any time throughout the session and will be addressed after all 3 presentations conclude. Our first keynote speaker is Dr. Tom Sugar. Tom's a professor at ASU working in the area of wearable robotics. He's been studying gait assistance for the ankle, knee, and hip. In his presentation, he'll describe the design of the exoskeleton tailored to the task of pushing and lifting objects onto large cargo airplanes. Dr. Sugar's presentation is entitled Exoskeleton Assisting Human Movement. And with that, let's start the presentation.
Good morning. I'm going to talk about exoskeletons assisting human movement. My name is Tom Sugar. I'm a professor here at Arizona State University, and this is part of the Prevention Through Design Workshop. For an outline, we're going to discuss why exoskeletons could be needed, how could they improve worker wellness, how could they reduce fatigue, assist the worker. So I'll describe different types of exoskeletons. Then I'll focus on the aerial porter exoskeleton here that we developed here at ASU. And then I'll do some conclusions. So what are we hearing? We're hearing that there's an aging workforce with a limited number of young people. So there's less people going into logistics, material handling, manufacturing. And we want to improve the long-term safety of this workforce. So how can we prevent long-term chronic injuries? We're hearing about people having shoulder injuries when they're working above their heads. They've got neck injuries and a lot of times lower back pain and lower back injuries. So we want to improve the quality of work, making it less fatiguing. So let's talk a little bit about industrial exoskeletons. There's different types of exoskeletons out there, but I'm going to focus on industrial exoskeletons today. So there's passive and active exoskeletons. So passive systems use typically springs or pneumatics, and basically you put energy into the system, or whatever energy you put in passively, then you get back out. And so these systems can help with lifting heavy objects, palletizing, or pushing heavy objects. So for passive system, you can imagine spring systems that help your shoulder when you're using tools above the head. Here in this shoulder X, you can imagine spring systems around the lower back to assist when squatting or leaning over or lifting. And you can imagine, again, a shoulder exoskeleton being used in an automobile plant. Excuse me. So there's technology barriers, but these barriers are being reduced. There's better batteries, there's better sensors, there's better actuators, and there's better microprocessors. So in this picture, you're now seeing an active exoskeleton that has a motor with this orange piece is a motor, and you can imagine you have a motor on the left hip and the right hip, and it allows you to lift objects that allows you to squat down and lift back up. And this is a Cyberdyne product being used at a Tokyo airport. So there's passive systems that maybe help you hold tools, and then there's powered systems. So if I look at the picture on the left, this is an exo push. So you can imagine a motorized rake that the person holds the rake, and then the motorized rake helps to push asphalt back and forth while you're making roads. You can imagine this device here on the right where you're holding a heavy object. So there's a counterweight behind the person, and you're holding maybe a 30 or 40 pound grinder. So let's talk about passive shoulder exoskeletons. These are being used in industry quite a bit now. There's a levitate spring system that's being used in Toyota, an ExoWorks vest being used at Ford, Shoulder X devices, excuse me, SkeleX has some devices, and Autobach has a shoulder device called Pexo. You can find many of the different types of exoskeletons at Exoskeleton Report or at wearablerobotics.com. If we think about passive lower back exoskeletons, again, you can think about spring systems that maybe attach at the trunk and attach at the leg, and they give you support around that trunk. So you can imagine when you squat down, you put energy into the spring, and then that energy is used, released to bring you back up. You can imagine here this HeroWare Apex device where you've got soft straps. So you can imagine elastic bands that go between the legs and the trunk, and then they support that hip area. There's ergo exoskeletons, so you can imagine a structure along the back that keeps you in the correct posture. Lastly, Pexo back systems, you can imagine systems that have clutches that clutch spring systems in and out when you need them. But here next, we've got powered lower back exoskeletons. So when you think about powered systems, they have a motor, and the motor can add additional energy into the person when you need it. Secondly, it could turn off and just be out of the way when you don't need it. Because many times some of these systems, when you're walking with them, they kind of are in the way a little bit, but they help you in the one task, squatting and lifting, but they're in your way when you're walking. But a powered system could be turned off when you're walking. So there's a Panasonic system, A-Tune, that's being used in factories. Hyundai is developing a powered hip system. Cyberdyne with this lumbar support system is supporting the lumbar, and then it's got motors on the left and the right hip. Inifis has pneumatic systems that give you a nice push when you need to, when you're doing squat lifting. Hexar out of Korea has got some motorized systems. Kubota has a system with motorized ropes that can help you hold objects and lift objects in agriculture. German Bionic has a system that can help you squat lift. And here at ASU, we made a Loadmaster system, and I'll be talking about the Apex system here next. So what are the goals of a powered system? It needs to seamlessly interact with the user. You don't want this exo gait where you kind of feel like you're walking through a swimming pool and you're being pushed not at the right time. You must not disrupt the gait cycle. You want just natural human movements. These systems need to pay for the weight penalty. So we're finding systems should be maybe 7, 8, 9 pounds. Otherwise, they're just heavy and bulky. And you want to be able to easily use them and not think about them. It needs to be what I was describing, and I'll say it again, something like power steering. When you turn to the right, it helps you move to the right. When you turn to the left, it helps you move to the left. Someone wants to put this system on and have it work, day one. So what are the challenges? Most exoskeletons are too heavy. They're kind of large and bulky. Most devices do not seamlessly interact with the user. kind of have to use tricks to get them to move. Some of them impair the motion. I described it feels like kind of you're walking through a swimming pool. You don't want to use standard robot controllers. You want to use systems like I described, where it puts energy in at the right time and just helps you assist the movement. So how do we overcome these barriers? Well, we've been thinking about storing and releasing energy in springs. We've been thinking about clutching systems where the system is completely disconnected when you're walking around and then connected when you need that push. We're using human-based controllers to pump energy into the human movement, respond to the human movement. We use phase controllers. We add positive energy into the movement like a power steering. And I really do think that's where we've got to be thinking about and working on in the future with these powered systems. They've got to interact closely with the human being. So we developed an aerial porter exoskeleton. I'll describe it and then I'll show a couple movies. It's portable, it's lightweight, it weighs about 7 pounds with the battery. It gives about 30 Newton meters of torque per leg. And we integrated inertial measurement units and a low-level activity recognition. So it knows when you're pushing and we assist when you're pushing, or it knows when you're squatting down and we assist when you come back up. But otherwise it's disconnected and it doesn't impair your motion when you're just walking around. We combine soft straps and rigid plates to create a structure. We have motorized joints. We have a motor on the left hip and a motor on the right hip, and we respond immediately to the human movement. And we add positive energy into the movement, just like power steering. So if we look at this aerial porter exoskeleton, we have a motor on the left hip, a motor on the right hip. We have what we call pelvic plates. We have a structure on the left side and the right side. And then we have these, what we're calling hip paddles. And so they push you at the right time. If we look at behind the back, there's no structure along the back. And we purposely did that because we found that people would get hot and sweaty if there's large structures along the back, and we wanted to be really comfortable when you lean over. So we just have a plate structure on the left and a plate structure on the right, a motor on the left, a motor on the right, a hip paddle on the left, and a hip paddle on the right. So we have microprocessors on each side. We have a main computer that's looking at inertial measurement units, and we have a small battery pack. So we tested this at the Travis Air Force Base, and we had aerial porters lift heavy objects and push heavy objects. So let me play a video here. And you can hear the motor turn on. So he's walking effortlessly. The motor turns on, and then he can finish the task. Push, push, push. So the motor just pushes when you need it. So let me play a video.
This device has really been used, really been tested. We actually got it out of the lab and worked on it at an Air Force base with aerial porters. It was not a lab demonstration, it was a real world demonstration to see when it worked and when it didn't work.
So the first time I tried it on was at ASU. When I put it on, I realized that there was more potential there than I thought there was originally. But their initial design of the suit was very close.
So we just load cargo on planes constantly, C-17s, C-5s, KC-10s, and 747s, civilian aircraft.
We kicked it off 8 weeks ago. We talked to airmen, hey, this is a prototype. We need all the feedback we can get. We need you to have honest feedback with us. Tell us how it is. That way we can make the suit better, so we're not giving airmen something that they're not going to use.
The fundamental purpose of the project was to work on worker wellness and try to make pushing and lifting safer. Because these people are pushing large objects onto airplanes. They're typically making large pallets, and then 4 people will push about a 10,000-pound pallet onto the airplane.
The heaviest lift was describing what the tests are. We're trying to get them actually out on the planes, see what it's like in the real world, how they react, because we don't want to give them something that's not going to help them in any way. It took a couple of weeks for people to really understand that, when we've got people on the plane, we need a pair, one person not wearing the robot, one person wearing the robot, so we can have a direct task comparison.
But by far, this experience was the most positive from top to bottom. They were basically requesting to use the device when they had heavy loads, heavy operations coming up, because they really did feel the benefit, both in, I think, the way it fits them. There's a comfort level there and a securement level that they gain, and then from the added torque that these actuators provide during those lifting and pushing tasks.
Helps with like stability, back stability, hip stability, and just your overall lifting technique. Even like your center of gravity. So a lot of times you just, whether you're fatigued or you're not, you're just not focused on your center of gravity. You're trying to get the mission done. So this has helped you focus on that point.
Because once it's on you and fitted you, it's extremely comfortable. You can wear it all day and it's no problem. The way they've designed the systems to engage and disengage when you need it to, it makes it all that more impressive.
The awesome thing was the people who had already worn the exoskeleton were giving pointers to the individuals who had not. So they had developed their own institutional knowledge of how to use the robot and caught on so much faster. Seeing their reactions as they wear it and them kind of pointing each other out for how to do stuff, and just absolute enthusiasm for everything. I can't think of really any individuals that were having a bad time with it.
There's actually people out here focused on that part of the job rather than just the hard work of it. They're focused on the labor part. They understand that the hazards of the job, and they're trying to lower them hazards and decrease them.
They've given us a lot of great feedback, and ASU's been very receptive to that feedback. And I think ASU legitimately wants what's best for the airmen, for the Air Force. And that's why they're working so hard and we're working so well together. The relationship has been fantastic. It allows us to create something that we could actually use.
In my viewpoint, the 8-week period went outstanding. We had many aerial porters wear the device, tell us how they liked it, tell us how they liked it, the feel of the device. It also assisted them. We also used it in real-world tasks.
So let me conclude that systems are being developed with the goals to reduce fatigue, lifting loads. Passive shoulder exoskeletons are being used in industry currently to working above your head. In the construction industry, there's a Hilti passive shoulder exoskeleton. There's passive back exoskeletons to reduce the loads on the lower back. And powered back systems are now being developed, and I think you'll see some of those in the future. If you'd like more information, you can look at wearablerobotics.com. I will talk with people later today. Thank you very much.
Okay, thanks for that presentation, Tom. That was really interesting stuff, and the implementation, the videos were really helpful.